in many ways quite similar to what you might be used to already. You start by writing the code in a supported language. That would be different depending on the blockchain implementation you are working towards. In this course, we will be using a language called Solidity, which is supported by the Ethereum, and it's currently gaining support in the Bitcoin blockchain as well. Another current option would be to write Serpent code, which also has some community support for Ethereum. After writing the code, it must be compiled to bytecode. There are several compilers available. There are even online compilers that will get you started quickly. In this course, we will use a framework for working with smart contracts that is called Truffle. Truffle has a built-in compiler that is very easy to get started with. When a compile is done successfully, we upload our contract and wait for it to be mined. After the contract is successfully mined, we can start interacting with it. In most cases, you would create a user interface towards the contract, but you can actually interact directly with it through HTTP post operations. So, let's talk a little bit about the tools that we'll be using in this and the next module. Firstly, the language. Solidity is an object-oriented JavaScript-style language. The idea for it came from Gavin Wood in 2014, and it was developed by the Ethereum project's Solidity team. If you have programmed with other object-oriented languages before, it's quite easy to get used to. Solidity has the possibility for normal inheritance, as well as multiple inheritance, and you will find the supported data types and coding structures quite familiar. Here you are seeing a very simple example of a Solidity contract. We will look into the details of the most used parts of the language in this module. I'll not go through all the different data types that is supported by Solidity, but let me name the most used ones to get you started. Booleans are supported with the keyword bool, and it can contain the constant values of true or false. Strings are also supported and are encapsulated with quotes, as you're probably used to. But string manipulation is currently very limited, and it really should be. This is to underline that you should really strive to do the most unnecessary work outside of the blockchain. Integers can be signed or unsigned, and they range from integers with 8-bit resolution to 256-bit. In an 8-bit integer, you can store integer numbers from 0 to 255. In an int 256, you can store numbers from 0 to 2 to the power of 256. Which is a very, very, very high number. You should be aware that if you don't give a size to the integer and only use the int or uint keyword, the maximum size will be used. Another really useful type is the address type. It can store an address used in Ethereum, for example to an account or a contract. This is useful in many ways, as we will see later. At the time of writing, Solidity does not support fixed point numbers, but it should be supported quite soon. When using the upcoming type, you must specify the number of bits you want to use for each part of the number, for example 8 by 8. In the current version of Solidity, you can work with decimal numbers and do calculations, but fixed point results must be returned as truncated numbers or integer arrays. And this again is really to underline the fact that you should really do only the most necessary things on the blockchain. Everything else should be kept outside. As with most other programming languages, we have access modifiers. Access modifiers are keywords used to ensure that your code only can be executed from where you expect. Public means that it can be accessed from everywhere. Private limits access only to this contract. Internal means that this contract and those contracts deriving from it can access the method or property. External will disallow internal access and make it only accessible externally. One important note though, everything that is inside a contract is visible to all external observers. Making something private only prevents the other contracts from accessing and modifying the information, but it still will be visible to the whole world outside of the blockchain. Here's an example that encapsulates some of the main structures of Solidity. Firstly, it's defined by using the contract keyword and the name of the contract we are using. Within it, we can have state variables and functions. Functions that return values define their return type. You should also be aware that you can have multiple return values in Solidity. Here you see that we have used the public keyword. This means that the function is accessible from all locations. Public is the default, so in this case it's really not necessary to define it. But I like to make it clear in order to avoid any unintended behavior due to my neglect. Now let's talk a little bit about Truffle. Truffle is a toolset framework for development, testing, and asset pipeline for Ethereum development. Truffle includes tooling to compile and build your solution. It enables a framework for automated testing, and it makes deployment of our contract very simple with support of configurable deployment locations. Another great thing about Truffle is that we can actually use it in console mode as well, in order to interact directly with our deployed contracts. This is quite cool, and I'll show you how it works shortly. When working with smart contracts, it is crucial that we know that our contracts really work as expected before we unleash them to the world, because we don't have a feasible option for doing a take two. Uploading to a blockchain test environment on the net will take some time. It is therefore very time saving to use a local test blockchain instead. TestRPC is an easy to use in-memory blockchain that is great for testing your contracts while developing. Not having to wait for an external blockchain will really speed up your development in the early phases. TestRPC implements Ethereum JS, which is the same set of instructions that you'll find in the real Ethereum blockchain. Another great thing about TestRPC is that it will automatically create 10 throwaway test accounts for you with the connected private keys. So in PowerShell, let's go ahead and make a folder for our project called Hello World. And let's get into the folder. We'll now call on Truffle to initiate our solution. This will create a simple framework for us, and it will let us get started quickly. There, the solution framework is created. Let's open it up in Visual Studio Code to see what we've got. If we look at the Explorer, we will see that it has created a structure and some plumbing files for us. Let's click on the Contracts folder and add a file called helloworld.sol. This will be our contract file. The first we want to do is to set a pragma telling the compiler which versions of Solidity our code will work with. We'll go ahead and set it to any version above 0.4.4. Then we'll create our contract called Hello World, encapsulated by squiggly brackets. We're now going to make a very simple function that is called say hello. That function will return a string. And then let's just return the string hello world. There we go. Hit Ctrl S to save the file. And the next we need to do is to create a script for deploying the contracts. This is the file that will tell Truffle which files to deploy to the blockchain. This file name must be exact, and we place it in the migrations folder. We will create a variable called hello world that will link to our newly created artifact file. And then we must add the hello world artifact to the deployer. Hit Ctrl S again to save the file. We can then switch back to PowerShell. Truffle has many great features. One of them is that it makes use of TestRPC, or Ganache as it's called now, to make it super easy for us to test and run our Solidity code. When starting, it will create a set of test accounts and private keys. The first account is what is used as the default account. We will start Truffle in development mode by using the development parameter. Here we see that we now have 10 accounts and 10 private keys. The development server runs at port 9545. We are now ready to deploy our contract to the test server. That's done by using the migrate command. There, our contract is now successfully uploaded to our blockchain, and we can see the address it got when uploading. We could now go ahead and create a user interface for our contract and test it out, but with Truffle, there's also the option of communicating directly with it. This is a very easy way to run the contract. In development mode, we are actually able to write JavaScript code directly to our contracts.
This takes some time to get used to though, as your commands will be executed as JavaScript code, line by line. Let's first define a variable called HW for easy access to our contract. Since the variable is not defined with a content yet, we get the response saying undefined. This is not an halting error at all, it's just information for us at this point. Then things get a little bit complex. Since working with contracts should always be done async, we must use async code to access our contract. The contract is referred to by using the deployed keyword, so we will access it with the hello world.deploy, and then use the then keyword to create an async function that will map the deployed contract to our previously created variable. We can now access our contract and methods directly on the variable by using the call function of our sayHello method. That's fantastic. I always get so happy when I see the hello world from the first program we're making in a new language. So, let's return to the slides for a while to see what else we can do with smart contracts. Let's spend some time looking into more details of Solidity. We start with structs. Structs are custom-defined types that can group several variables, like in the example here, where we are defining some variables on a person structure. Structs can also contain other structs, like you would expect. Enums is short for enumerated types and can be used to create custom types with a finite set of values. This can really make your code easier to read. But you should be aware that when you return an enum, it will actually only return the integer value associated with it. Arrays is a data structure that contains a group of elements. These elements must be of the same data type. Arrays can consist of native types like string and integers, or they can consist of more complex types like structs. Arrays can be dynamic, like the two top examples, or they can be of a fixed length as shown in the last line. Arrays are assigned or read by using the index of the element you want to access. For arrays and structs, you have an additional annotation that will set a data location. Data locations change how assignments behave. Depending on the context, there is always a default, but it can be overridden by appending a keyword to the type. The default location for function parameters, including return parameters, is memory. The default for local variables is storage, and the location is forced to storage for state variables. The third data location is call data, and this is a non-modifiable, non-persistent area where function arguments are stored. External functions, input parameters, but not return parameters, are forced to call data. And for all practical purposes, for us it behaves like memory. Mappings is a very usable structure that we can use as well. A mapping will map any type to the index of another type. A very common use for it is to map addresses to values, like in the example here, where we have a list of currency balances for an array of addresses. When accessing it, you use the type defined to access it. If you are used to writing C#, you can think of mapping tables as dictionaries. The only possibility that the code is removed from the blockchain is when a contract at that address performs the self-destruct option. The remaining ether stored at address is sent to the designated target, and then the storage code is removed from the state. Using the delete keyword is a good way to clean up a contract and delete all stored data for the variable. This is a little less drastic than to self-destruct the entire contract. If condition checks fail or something goes wrong in your code, you can use the throw command to stop all operations. This will return the ether that is not already spent to the caller. Using conditional throws is a much more recommended way to stop your contracts from working than to use the self-destruct option. One way to do this would be to implement a bool as a private state variable in your contract base and use throw if it is set. This would keep the contract in place and keep data already stored intact, but render it useless for new executions.
Comments are supported in three ways. You can use double slashes for single-line comments. We use /asterisks for multi-line comments. And Solidity even supports the use of NatSpec type of comments. These are marked with 3 slashes. We will not go into the detail of this now, but with this type of commenting, you can, for example, generate metadata for your contract facades. We'll start back in PowerShell. In this demo, we will be making a contract for keeping scores. So let's create a directory name called score store. And let's get into the directory and use truffle in it. Once that's done, we'll open the current folder in Visual Studio Code. And again, we see that the plumbing has been made for us. So let's create a new contract file called scorestore.sol. As always, we begin by setting the pragma for Solidity so that we know exactly how our code will be executed. Then let's make the frame for the contract. To store the scores, we will be using a mapping variable that maps a string to an int, and we'll call it person scores. Now we need a function to add a person to the score, so we'll make a function called add person score, and it doesn't need to return anything. It should take a name as a string and a starting score as parameters. Inside the function, we want to add the values to the mapping variable. Next, we want to add a function for checking the score of a given person. We'll call that getScore, and it takes the name as a parameter and returns the score as an int. It accesses the person scores mapping and returns the value directly. This should cover the functionality that we want for this contract. And again, as we did in the Hello World example, we want to go and create a deployment file. And as always, we need to get the artifact for our contract. And then we'll add it to the deployer. Now ensure that all your files are saved, and we can go back to PowerShell. Let's go into truffle development mode. Let's call the migrate command. There, the contract was migrated successfully, and we'll make a variable to make use of our contract. We'll call that variable SS and add an ASIC handler to it. Now, let's try to add a person to our score store. And just to make sure, let's make a call to the method to see if our score actually got stored. Excellent, that seems to work great, and we are getting the score back. Now that we know that our code works, it's time to publish it to a real blockchain. We will use the blockchain that we created earlier. To do that, we need to do a few steps. First, let's exit the truffle development and go back to Visual Studio Code. If you look at the Explorer, you'll see a file called truffle.js. Go ahead and open it. This file contains the definition to the deployment locations. Here we can define our production network. We now need to get the address to our production blockchain. To find it, we go into the Azure portal and find the deployment page for our blockchain. Here we want to copy the address to the Ethereum RPC endpoint. We'll go back to code, and we'll enter it as host. We must also remember to remove both the HTTP part of the values as well as the port number, since this is defined in a separate setting. Next, we must give the network ID that we created the blockchain with, and then the port. And then we must tell Truffle from which address we will be deploying, since actions will cost either. Use the default account that was created for you. This is the same account you will find at the top of the admin page for our blockchain. The last we need to define is the gas we will be using. Hit Ctrl S to save the file, and let's go back into PowerShell. In order to be able to work on our production blockchain, we need to access an account that has Ether. The default account that was made for us has a lot of it, but by default it is locked down for obvious security reasons.
Luckily, there is an easy way to get the account unlocked so that we can use it to upload and communicate with our contract. To do this, we'll make use of the Geth client running on one of our nodes. We can connect to the node by using an SSH command that is listed in the output section of our deployment. So, go back to the Azure page for our deployment. Copy the value from SSH to the first TX node region 1. And go back to PowerShell and paste it in and hit enter. You must now enter the password you used when creating the blockchain. We'll then do a geth attach to attach to the Geth client. Geth is a JavaScript console that enables us to send commands directly to the blockchain. What we want to do now is to unlock the default account so we can do transactions with it. So from here we can call the unlock command. This will unlock the default account. Please note that you must use your own password here. This will unlock the account for external usages. Please note that you should remember to lock it when you're done, since it is now open for the world to exploit if they have access to your blockchain admin page. Now let's exit Geth and SSH. We are now ready to run Truffle, but this time we'll not run it in development mode. We will run the console mode towards our production blockchain. We can now use the migrate command to migrate to our production blockchain. There we go, our contract is now uploaded and running. Now let's use our contract the same way we did earlier to check that everything is well. Again, let's make a shortcut to our contract. Let's make a call to the add person score, and let's call it with a different name this time. As you might notice, transactions take a lot longer time on a real blockchain than when using TestRPC or Ganache. So, using TestRPC during development will save you a lot of time. Anyway, our transaction is now mined and we should be able to get the values back as well. To see that the values can be returned, we'll make a call to the getScore function. There we go! Our score store contract is now running on a real blockchain and is ready to use. With Ethereum, we can actually do external calling of functions as well. Let's say we have contract A and contract B. Contract B has some functionality that we want to make use of in contract A. With Solidity and Ethereum, we can actually make a call from contract A to contract B. Let me show you how calling external contracts actually works. We will go ahead and create a second contract, and we will call our first contract from the second contract. Let's head over to Visual Studio once again. Now, to show you how we can use external contracts, I'll just want to make a very simple example for you so that you can see how easy it really is. We will create a contract for a specific game that will use our score store contract to keep track of the game score by making external calls to it. We will create a folder called My Game and do a truffle in it. And then we'll open it in Visual Studio. We'll then make a contract called mygame.sol. Let's add the pragma and the contract structure. We are now going to create an interface that will resemble the contract we made earlier. This is necessary in order to tell Solidity about the structure of the contract we will be using externally. We will call our interface iScoreStore. Our interface does not need to have all the properties and methods of the original contract, only those we will be using. Since we will only make use of the getScore function, we'll make a placeholder for that. Now we will create a method that uses the score stored contract that we deployed earlier. We name the method on our contract showScore and let it accept a name. We must now create an instance to our interface. We will call that instance scoreStore. The interface accepts an address to our existing contract as a parameter. To find that address, we open up our scoreStore contract in console mode in a new PowerShell. Make sure that you are in the right directory. By using the command scoreStore.deployed, we can find and copy the address to our deployed contract. Here we go. Let's paste that into our MyGame contract. We can now make a method call to the getScore function and return the value. Hit Ctrl S to save the file. Now we need to set up the deployment location to production. Again, you'll find the values in the Azure portal. We will be using the same values as we did in the previous example. And of course, we also need to add our new contract to the deployments. Follow the same structure as always. We load the artifact and we add it to the deployer. Remember to save, and let's get back into PowerShell. Let's open up Truffle in console mode, and we can migrate. There we go. Let's just quickly create a variable for the contract. Point it to the deployed contract. Now, in order to call the method and get the value to the console, I'll write a simple call that takes the return value and calls the console log method. We see that we are using the same person name that we used when we tested out our previous contract. There we go, see that we get the expected result, and we have now created a contract that uses another contract to do its work.
In this module, we have gone through the basic concepts of Solidity. We then did what we always do when learning a new programming language. We made our first Hello World contract. After that, we looked at some important aspects like mappings and arrays, before we created a contract that does blockchain storage and pushed it out to a running blockchain implementation. Right at the end, we made a second contract, and I showed you how to do external contract calling. Now that we have looked at the basics, let's jump over to the next module, where we will be creating a simple but full application that lives on the blockchain.